Hello and welcome to Discovery at Home. My name is Jillian and I'm a science educator at the Discovery Center. I'm excited to be streaming to you live today so you can continue to learn new things, interact with us at the Discovery Center, and the best part of all, of course, to have fun with science. Today's workshop, The School of Hard Rocks, is, you guessed it, about rocks. But we can't forget minerals too, of course. In a little while, longtime colleague and paleontologist Sabrina will walk you through the rock cycle and show you some different rock and mineral samples before you head off for your own scavenger hunt and classification. Typically, when we think of scientists who study rocks and minerals, we think of geologists. But paleontologists like Sabrina also need to understand the science of rocks because they study ancient plant and animal life through their fossilized remains, and fossils are rocks. When I was a little kid, I was always interested in scavenging beaches, parks, and playgrounds for pretty rocks, or at least what I thought were rocks. I looked for anything that was sparkly like a crystal or metallic looking. But those shiny finds that I thought were rocks were actually minerals. They're minerals because they contain only one type of chemical compound instead of a combination like we find in rocks. Minerals happen to be my favorite part of this workshop, so to get us started while we're waiting for others to join the stream, I'll show you some of my favorites. Here's a sneak peek at a few minerals in my collection. All right, our first sparkly gem is a quartz crystal. And I also have a larger version I'll show you in just a second. So our quartz crystal is nice and shiny there. Here is our larger version. And quartz is one of the most well-known minerals. It's found in basically all mineral environments worldwide. Quartz has the most varieties of all minerals, so we can find quartz with many different colors and clarities. The quartz group also includes a well-known purple variety that we can find here in the Maritimes, especially in the Cape Split and Cape Blomidon areas, including Amethyst Cove. Do you know the purple quartz that I'm talking about? I've actually already given you a hint. This purple gemstone I'm talking about is called amethyst, and Sabrina will show you some later on. The next mineral in my collection is one of my favorites, and it's the reason we have the term fluorescence, because it glows or fluoresces under UV or black light. Here's my mineral. This blue-green to purple specimen is called fluorite, and under a black light it glows a purple color, similar to the way a white t-shirt glows during a glow-in-the-dark mini golf session or a cosmic bowling party. My next mineral is one that we can technically eat in small quantities. Any guesses what it might be? This mineral can be mined in solid chunks and is made of sodium and chloride atoms arranged in cube-shaped crystals. Let's have a look. We usually grind it into fine grains and use it on our food. Now do you know what it is? Geologists call this mineral halite, but more commonly we call it rock salt. Halite is usually colorless or white, but sometimes we find different colors because of other materials or impurities mixed in. One example on my table is pink Himalayan salt, which you can commonly buy to sprinkle on your food or can find as decorative salt lamps. The pink color comes from trace amounts of other minerals like potassium, magnesium, and calcium. My last mineral for now is pyrite, also known as fool's gold. Let's have a look under the microscope. There we are. This mineral has a characteristic cube-shaped arrangement. Can you see that? Look at the tiny cubes under the microscope. If you find something similar to this and want to know if you found pyrite or real gold, an easy way to tell is seeing what color streak it will leave behind. The streak test is a common test geologists use to help identify minerals. You can do this test by scratching your mineral sample on a porcelain tile, also known as a streak plate. Both of these minerals are softer than my porcelain, so when they're scraped against it, they'll leave dusty bits of the mineral behind. Real gold will leave a gold-colored streak, but pyrite does not. Let's have a look. Instead, it gives a black-colored streak, quickly letting us know we won't get rich from our treasure hunt. There you have it. All right. Since today's activity includes a rock scavenger hunt, I will let pyrite be the first sample for you to find. Watch closely as Sabrina shows off her rocks and minerals to you, because somewhere in her video there is a small pyrite sample. See if you are observant enough to catch it. For those of you who have tuned in late, thanks for joining us and welcome to the School of Hard Rocks workshop. My name is Jillian and I'm a science educator at the Discovery Center. We're almost ready to dig deeper into the workshop, so let me formally introduce today's topic. In today's workshop, we will focus on ways to classify rock and mineral samples like a geologist by sorting them based on their attributes and features. You'll go on a rock and mineral scavenger hunt to find your own sample to classify. This could be anything from samples found outside in nature, things built from stone or carved from minerals, for example, buildings, statues, or even jewelry. Before we rock on over to Sabrina, I want to remind you to share your science after completing today's activity. Today is the last day for submissions to our Show Us Your Science contest. When you send in your rock and mineral classifications or show us what you found during your scavenger hunt, you'll be entered in the draw for a Science at Home prize pack. Results can be shared on Flipgrid, Facebook, and Twitter. Don't forget to tag the Discovery Center, and best of luck to you all. Now it's time to rumble on over to see Sabrina and some of the nice geological samples she's uncovered.
Hi folks, I'm Sabrina and I'm a science educator and proud geology nerd here at the Discovery Center. Welcome to today's workshop, the School of Hard Rocks. Today, we're going to go on a science scavenger hunt to see what geological samples we can find around us and to learn a little bit about how we can classify them. Let's dig in and get started. Rocks and minerals quite literally make up the world around us. Not only that, they tell us the story of Earth's history, grain by grain, boulder by boulder, and layer by layer. Whether looking at the smallest crystal or the largest continent, geologists can use their study of rocks and minerals to understand how our planet and others in and outside of our solar system was formed and how it's changed through time. But what are rocks and minerals? How can you identify and organize them? And what sort of information can you learn from them? Geologists rely on several different techniques to gather information from rocks and minerals. One of those techniques is classification, which basically just means grouping together similar samples to find patterns in their appearances, textures, and other qualities. At its most basic level, geological classification defines two groups: minerals and rocks. Let's start small with minerals. You need only take a look at these giant selenite pillars from the Cave of Crystals in Mexico to know that minerals are not always small in size, but they are the smallest component or ingredient of rocks. Now, a mineral is made of a single substance that's usually organized in a framework called a crystal structure. If we looked very, very closely with some very special equipment at our giant selenite crystals, we would find calcium sulfate, a type of salt, organized in a very careful, repeating structure that looks oddly like the framework skeleton of beams and connectors that supports a skyscraper, kind of like you can see from this image of the framework for the Halifax Central Library. The selenite framework yields a lustrous, shiny, generally clear crystal. What am I talking about? I have one right here. So here is satin spar, and we also have some smaller pieces of selenite as well. Selenite gets its name from the Greek word for the moon, and it's very, very soft. Check it out. I could even scratch this guy with my fingernail. Now, if the salt molecules inside of our gypsum selenite were organized in just a slightly different way, we would instead end up with gypsum alabaster. So I'm just gonna scoop these guys out of my way to pull over these characters. So alabaster is a soft, pearly mineral that resembles marble, like this guy right here. And alabaster is very easily carved, as you can see from this cameo, and it was widely used to make religious statues and art throughout medieval Europe. Now, these are just a couple of varieties of a single type of mineral, gypsum, but there are dozens of different classes of minerals, some of which can have over 100 varieties, yielding a grand total of over 4,000 known minerals in the world. And humans have used minerals in a number of different ways throughout history, depending on their properties, their attributes, and so forth. As an example, I brought in some jewelry and decorations. All right, now this is a piece of amethyst geode from the North Mountain basalt here in Nova Scotia. It's a type of quartz. I've also got an amethyst ring and amethyst earrings. Now, all three samples are sparkly, shiny, purple crystals that are easily polished but tough to break or fracture. These, on the other hand, are jade. So I've got a jade necklace and a jade ring from British Columbia, whereas this little guy is a jade sea turtle attached to a jasper egg from North Carolina. From these, you can see that there are differences between samples of the same type of mineral. Both the ring and the necklace are a type of jadeite, so they're uniform in color. So they're green. Pretty, but just green. While our sweet little baby from North Carolina is nephrite jade, and it has extra little impurities that have snuck in, and those give our jade delicate little streaks and waves of brown and tan. Now, it's pretty clear that I love minerals and their scientific properties enough to wear them. Now, rocks are pretty great too, though. And when two or more minerals combine, they form a rock. The type of rock that's made depends on what minerals the rock contains, the conditions it was formed under, including temperature and pressure, and how long it takes to form, grow, and change. To best understand rock types and how they relate to one another, geologists tend to organize rocks into three categories or classes based on these conditions. And those are igneous, sedimentary, and metamorphic. No matter what class a rock belongs to, it can be melted, broken up, heated and squished, or otherwise changed to become another type of rock, meaning that a rock's materials can be constantly recycled. We call this process of recycling the rock cycle. And you may have heard of the water cycle before, which is how water is recycled and carried all around the world. Well, the rock cycle does something similar, but with rocks and minerals. Let's explore a couple of examples of each class of rock, discuss how they're formed and changed by the rock cycle, and compare some of their attributes and how we use them. Let's start off with igneous rocks. Igneous rocks are made when magma, melted rock deep below the Earth's surface, rises and begins to cool and harden or crystallize. Different igneous rocks will be formed depending on how quickly that magma cools. When magma cools slowly in layers below the Earth's surface where it stays relatively warm, it forms rocks like granite, which contains large, beautiful crystals that have had plenty of time to grow as the magma slowly cooled. Granite is pretty tough and hard, which makes it durable and long-lasting, great for building structures and even countertops. Now, when the magma goes above the Earth's surface, such as during a volcanic eruption, it can cool so quickly and so smoothly that it looks like glass. This volcanic glass is called obsidian, and it can be very sharp, which has made it useful throughout history for folks making tools, spears, arrowheads, and knives. Now, when the volcanic eruption is very violent, it will shoot magma into the air where it combines with volcanic gases and the air itself and cools almost instantly to create pumice. Pumice is a rock that looks like and is sometimes used as a bath sponge, with plenty of gas pockets that make it light enough to float on water. Next up, we've got sedimentary rocks. Sedimentary rocks are formed when existing rocks that are broken down through erosion, usually from being weathered by flowing rivers, ice freezing and thawing, and rain, begin to collect when they're deposited. These deposited sediments get squished or compacted as new layers of sediments get piled on top of them, and they're glued together by a mineral or muddy cement that fills the spaces between them. Sedimentary rocks are usually defined by the size and shape of the sediments that they contain. Conglomerates, for example, are a sedimentary rock with smooth, polished, well-weathered pieces of large sediments, sometimes very large, sediment as big as boulders. Now, our studio is pretty big, but it isn't big enough for a really impressive piece of conglomerate, so I've got this little sample right here. Conglomerates can contain a wide range of different types and sizes of rocks and mineral. Sediments all glued together, usually by a muddy cement. And since conglomerates are not the same throughout, their characteristics depend on where you're looking within the sample. In one spot, you might have tough granite, and in another, crumbly clay. These differences mean conglomerates are not very useful as structural building materials, but because of how beautiful they can be, they're often polished and used to decorate buildings. Now, sandstone, on the other hand, is formed from sand-sized sediments. So materials that are much more weathered, eroded, and worn down than those that make up conglomerate. When sandstone is red, like this guy right here, that tells us that the sediments were deposited by wind or during a flood where the water levels later dropped. Being left out in the air gave the iron in the sand lots of time to rust, making it red. If it had stayed underwater, it wouldn't really be affected by the air, so it would have stayed gray. Sandstone is usually made up of sand, just sand, so is similar throughout. It's relatively easy to cut and handle and pretty sturdy, though definitely not as durable as granite. Since it's pretty hard, easy, and inexpensive to handle, and it's also pretty common, it's everywhere, we use sandstone all the time when building structures. And we often have to replace sandstone blocks in high traffic areas, like on the stairs where they might get worn down by people's feet. But that's usually decades down the line. Our last class is metamorphic rocks. Metamorphic rocks are formed through change, or metamorphosis, when existing rocks are buried deeply enough under new deposits of sediment and rock. They're heated and compressed so much that their color, texture, and hardness can change completely. The large, rounded minerals of granite, an igneous rock, are compressed into lines and waves when it's transformed into gneiss. If granite is hard and strong, you can only imagine how durable gneiss is. Gneiss' toughness makes it difficult and expensive to cut and shape, so it's usually only used for decorations, like the wall tiles in the fanciest bathrooms, or for things that you want to last as long as possible, like gravestones. Looking at a sedimentary metamorphosis, on the other hand, the sand in sandstone, like this guy from before, becomes pearly, shiny, and polished when it's heated up and compressed into quartzite. Quartzite is beautiful, and while it's harder than sandstone, it's still very possible to carve and polish it, which is why it's been used to make statues for a long time, like with this enormous statue of the pharaoh Tutankhamun from ancient Egypt. Just like the water cycle recycling water, the rock cycle is great at recycling materials, so rocks are not locked in stone, pardon the pun, and can change when the conditions that they're in change. As you saw from some of our examples that we just explored, an igneous rock like granite can be eroded and become part of a sedimentary rock like conglomerate. Or it can be heated and changed to become a metamorphic rock like gneiss. It can even be completely melted and crystallized to become a new igneous rock, even a new granite. Because of this recycling, rocks act as a snapshot, a moment frozen in time that can tell geologists about the conditions that existed when that rock was formed. As long as geologists stay organized and keep an eye out for patterns and characteristics in their samples, they can reconstruct the history of the world, more or less. Now it's your turn to become geologists and collect some samples from around you. Examine your samples to identify key features and qualities and sort them into groups that may help you pinpoint some patterns. You'll want to gather 5 to 10 different rocks or minerals to use as geological samples. Do your best to find physical examples like these ones so that you can gather as much information as possible. These physical samples could be jewelry, like some of the stuff that I showed you from before, or statuary, like my little jade sea turtle. It could be countertops, rocks from a garden, boulders on a hiking trail, or stones used in the buildings around you. If you need to find some more samples, you can also use images that you've taken yourself in the past, or information and photos that you can find from safely searched websites. And some of your samples could even be the rocks and minerals that I've described in our workshop today. You'll also want to have a piece of paper or the chart that we've provided in the learning guide, as well as writing materials to record your observations. You'll need to clear yourself a little bit of space on a table, counter, or even the floor to organize your physical samples into their different groups. And finally, you should gather some tools to help you explore different features of your samples, such as a magnifying glass or the field lens, like I have right here, as well as some tools to help to compare hardness, like a penny, a steel nail, or even your own fingernail. Once you've gathered your samples, identify the features that your samples have. Record what you observe. While geologists talk about the similarities and differences between rocks and minerals, or between the 3 classes of rocks, there are many ways to group your samples. Geologists might describe rocks and minerals based on their color, shininess, smoothness, hardness, how we use them, and how they were formed. What qualities do you notice first in your rocks and minerals? Try to find similarities and differences between them. Then, sort your samples into different groups based on those features. How many groups do you end up with? Are there different ways that you could group them? Did you find it difficult to place any of your rocks and minerals into a single grouping? And what patterns do you see between your groups? Once you've had a chance to work out your groupings and how you want to classify your samples, I'll be back with a curveball. I am going to give you a top secret, super mysterious sample that I'll want you to fit into your existing system. So keep this extra layer to your challenge in mind as you make your groups. All right, friends, we've basically taken a journey to the center of the Earth and have explored many different ways that geologists look at the world through the lens of rocks and minerals. Good luck with your sampling and sorting, and I'll be back with another sample to both challenge you and help cement what we've learned about geology and classification. Until then, I hope you're able to excavate some amazing science.
Thanks, Sabrina. I really enjoyed learning more about rocks and may have a few more minerals to add to my favorites in my collection. Viewers watching the stream, were you able to spot Sabrina's pyrite sample that I mentioned earlier? She actually had 2 small pyrite samples. They were worn as jewelry, her earrings. Great job to anyone observant enough to catch them. All right, friends at home, it's almost your turn to go on your scavenger hunt, but first I want to remind anyone who has tuned in late and missed parts of the workshop that you can rewind anytime during the live stream. Right now is a good time to rewind and watch the content you missed, especially if you missed Sabrina's walk through the rock cycle and explanation of today's classification activity. You can also find the learning guide, including the classification table, on our Discovery at Home webpage. Once you've found and classified your samples, reflect on your criteria by sharing the objects you found with us and tell us why you organized them the way you did. If you have questions during your rock hunt or classification activity, please reach out on the Discovery at Home webpage or send us a Flipgrid video question. Our team of educators are here to help you out. Before I go, don't forget to share your science with us to get in those last entries for our Show Us Your Science contest. Every time you share your science, you will be submitted into that draw for a Science at Home prize pack. You can share your results anytime before the end of today. And if you'd like your results featured in our live show, remember they need to be submitted by 5 minutes to 11 a.m. I'll see you again at 11 so we can classify a few more of my favorite finds and check out your amazing samples. I'll see you again real soon. Hello and welcome back to the School of Hard Rocks workshop. If you're tuning in now for the first time, my name is Jillian, and today on Discovery at Home, we put on our geology thinking hats to classify rock and mineral samples. From beach stones to buildings, rocks and minerals are all around us and definitely under us, making up the Earth. So with that said, I'm excited to see your finds. If you haven't already tried today's activity and submitted your classifications, it's not too late to get in your last entry to our Show Us Your Science contest. You can submit any time before the end of the day. You may choose to go do that now or stick around to see what others have found first for a little bit of inspiration. Let's check out our first viewer submission. This was sent in by Nora, and Nora's got a really cool looking rock and mineral kit here.
Hi, so I have my own rock collection right here, and it came with a magnifying glass and this cool light marker, and you use the marker and the light. So you would usually write something on a rock, close it up, turn on the light, and then it's like your own secret message. And I'm going to show you one of my favorite rocks with my magnifying glass. And I have lots of different kinds of rocks. And bye.
Great job, Nora. Thanks for sending that in. It was a really cool kit, and it was neat to see that you had something to write that secret message and use a black light to see it, kind of like my glowing fluorite I have here. I really like that you used your tiny little magnifying glass to look at some of the characteristics of those rocks and minerals, and probably that will help you classify. It certainly helped me see them a little closer and see if they have crystals or some of their colors and textures a bit better. Great job, and thanks for sending that in. Let's check out our next viewer submission, see what they've sent us. We've got some lovely looking beach finds sent in by John Mack, and they look like they're all very smooth looking objects, and I have something here I'll show you in a minute too that you might be interested in if you like beach combing. Let's check out the video. So we've got some organic, some once living things, and some inorganic things that have minerals. Some handmade and some natural things. It's a neat way to classify, looking at living things and inorganic things like our minerals, which would fall with our rocks and minerals today. And even some human-made things in there that were made possibly by rocks and minerals, like our brick. We're getting some color in there to help us classify. Awesome job. Many different ways of classifying. As we can see, we looked at colors, textures, whether it was human-made, man-made, made by nature, or just geological finds like the earth itself kind of churning up those rocks, making them jagged, or different colors because they had different mineral content. I also have something you might find a little interesting. I found this on Dominion Beach in Cape Breton, Nova Scotia, and does anyone know what this might be? It's a lot smoother than it normally looks, but it's actually a piece of coal. So we use coal to burn for fuel to help us create energy, to create lights, power. But this is neat because it's washed up on the beach and it's become very smooth. And it's neat to think that coal, even though it's organic, like some of the other things you found, like your beach driftwood actually came from living things. Way back in the Carboniferous period, plants were buried under swamps, and those plants over time and compression turned into one type of rock. Do you remember which rock Sabrina talked about that forms from many different layers and pressure? If you forget, that's okay. It's a sedimentary rock, and coal is actually an example of an organic sedimentary rock. So we can use that organic fuel trapped inside to help us create power. Really cool, and this was a nice beach find that I couldn't help but scoop up one day. I thought it was quite interesting. Let's check out our next viewer submission. This one is really gorgeous, and Michelle Arthur sent this in saying it was a sample that she bought in Portland. We weren't sure if this is Portland, Maine or Portland, Oregon, but our best guess, or Sabrina's best guess, I should say, is if it came from Portland, Maine, it's likely an agate geode. Now, if you're not sure what a geode is, I used to buy these all the time as a kid. It's a rounded rock-like structure, and inside you often find lots of crystals, like you can see right in the middle there. So I'd get out my hammer and I would kind of put on my safety glasses, put it in a sock or something so shards wouldn't go flying, and smash it open to see the treasures that are inside. Always lots of fun when you find a geode. So great job for sending that in. I think it's gorgeous, so thanks for sharing. Our next find was from Niko, and Niko's got one of the rocks that Sabrina mentioned. See if you remember which kind of rock this falls in, and I think Niko actually will tell us.
Hi, my name is Niko. I have this rock. Its name is Obsidian. It's mineral-like. It's volcanic glass. It's translucent. It's a mineraloid and fine volcanic area. Bye.
Thanks, Niko, for sending in that obsidian. I usually only ever see it in tiny little pieces that we use for some of our workshops at the Discovery Center. So it's amazing to see a really nice big piece of obsidian. That's really exciting that you have that. Those of you listening, did you notice what kind of rock it was? He mentioned volcanic activity, so this makes it an igneous rock, and it's turned into a very glass-like structure. So we can use it to make sharp instruments. Even surgical tools can be made by obsidian, which I think is fascinating. Let's check out our next submission. This was sent in by Daniella, and she's got a lot of really pretty minerals to show to us today.
Hello, I am Daniella. I'm going to be showing you some rocks that I want to show you. Here we have obsidian. Obsidian is an igneous rock. Here we have citron. Citron is a mineral. We have pyrite. Pyrite is also a mineral. This is blue agonite. Blue agonite is a mineral. Blue agonite is a mineral. We have halite. Halite is a mineral. Here we have island spar. Island spar is a mineral.
Thanks, Daniella. Really interesting seeing your minerals. There are a few in your collection that I don't have in mind, so I'll have to see if I can find them. I like that you did mention that each of them were a mineral to help us get thinking about their chemical composition. What other ways could you classify them? Texture, color, think of how you might group your finds to help classify them just like a geologist. I also had a few questions come in, and I did notice over the break a few submissions rolled in on Flipgrid later on. So I encourage you all, if you haven't already watched them, have a look at see how others are classifying their amazing finds. I think there are about 4 more on there now, so it's really exciting to see how excited you are about geology in our province. I do have a couple questions to address as well, and one question here was from Matt, and Matt was asking, how can rocks help us find out how old the Earth is? This is a really great question. It's kind of a long answer, but we can help you out with this. So scientists will look for the oldest rock on Earth in order to try and date the planet and figure out just how old it is. But you can imagine finding the oldest rock can be pretty difficult. There's a lot of layers to dig in, and we know that through our rock cycle, rocks are always being recycled, from being melted down by magma and spewed back up to the surface as potentially something different. So you can imagine how tough that is to find. But scientists have found some very old rocks to help us kind of get an estimate. And it looks like the oldest rocks that we have found so far were found in the Canadian Shield. they were about 2.5 to 4.3 billion years old. Now that's pretty old, but they were found right at the surface. And I can imagine that things at the surface are probably not the oldest rocks on Earth. So to help scientists further along their estimates, they can look at other things outside of our planet, like the moon, for example, or meteorites. And doing that kind of analysis has allowed us to date the Earth at about 4.5 billion years old. But the kicker, that's give or take 50 million years. So we have a better estimate by looking at things around us and some of the older rocks we can find on the Earth as well. Another question that came in was relating to bone and pearls. And this is a really good question. Are bone or pearls rocks? Now, while both of them have mineral content in them, just like a rock, bone is actually living tissue. So inside bones, we do have minerals. Of course, we have calcium and phosphate to help our bones be very strong. But we have living cells as well, little cells called osteoblasts that make the bone. So short answer is no, bone is not a rock, but it has properties that make it kind of like a rock. Minerals, for example. We have a crystal structure called hydroxyapatite in our bones, hardening them and strengthening them. But they're not quite as strong as some rocks out there because remember, our bones need to help us move and they actually need to be a little flexible in order to do that. As for pearls, they're actually considered a mineral. They're made mostly of calcium carbonate, similar to my seashells here. So calcium carbonate is a mineral structure. So even though pearls are really hard and look like a rock, they're actually much simpler and are just a mineral. So thank you to everyone who sent in those finds. It's always really exciting to see the results of a good beachcomb or really any trip out in Mother Nature. I have some samples here today for classification to show you in my chart ready. There are so many different ways that I could classify. I could sort by physical appearance like color, texture, or the color of the streak left behind on my streak plate. I could even check to see if some rocks or minerals will react with certain chemicals like vinegar, a weak acid, and sort them based on that. I chose to sort by streak or no streak using my streak plates, which also relates to their hardness. Minerals or rocks that are harder than the tile streak plate won't leave behind any powdery residue when I scrape them across, and could even scratch the tile if they were hard enough. I can think of one example that would do this, and that's diamonds. Diamonds are extremely hard. So let's check out what I have here and see where they stack up. So I've got one kind of dark looking mineral. It's a bit shiny, it's a bit metallic. I do notice something else interesting about this. I have a magnet, and it's also magnetic. So what I have here is magnetite. It is a magnetic rock found, or magnetic mineral found on our Earth. Let's see what happens with the streak. I'll try the light plate since we have a dark sample here. So I'm noticing right away I'm getting a black metallic-y colored streak. So I could use that as one of my attributes. It creates a streak, and my streak is that black color. All right, we already saw my pyrite gave a similar streak earlier. My next mineral is hematite, and I noticed that it's got some sparkly texture in there. It's a grayish color. It's got a few red-looking streaks on there as well. Let's try it on the streak plate and see what we get. So even though it's similar in color to the magnetite, it's given me a much different color. It's like a reddish brown hue on the streak, indicating it is a different mineral and another way we could classify it by that streak color. All right, I'll give it a flip over to a clean side and we will try out our quartzite right here. Okay, so another mineral, we can see all those little cubic crystals, and we'll see if we can get a streak. Probably pretty hard to see on the white, so let's go with the black. So I'm getting a powdery white streak on that one. Okay, so another way I can sort that by streak color if I wanted to add a third category instead of just streak or no streak. I'll also try my quartz that I showed you earlier. Let's see what happens with quartz. I've given this a wipe so it's clean. See if we get a stripe. not really anything happening there, which means my quartz is probably much harder than the other one that I looked at here, my calcite. All right, my last one on the chart is diamond. I already mentioned diamonds are really hard. I don't want to ding up anybody's fancy jewelry, but I don't imagine that I would actually get much of a streak on here because it's incredibly, incredibly hard, probably much harder than my streak plate itself. So I want to show you one last favorite mineral of mine before we move on. My last mineral is calcite, and this mineral is really common throughout the world and is found in all of the 3 classes of rocks that Sabrina chatted with you about. It's also the main component of limestone and marble, and even those pearls that somebody mentioned earlier. Calcite is made of calcium carbonate, and we find these in seashells and the skeletons of marine creatures. So I've got some calcite here. I'm going to give it a nice scrape on here, try and get some powder going, and then we'll add a weak acid. We'll see if we get any bubbles with our vinegars. Whoops. All right, so I've got a lot of little powdery content on there, and maybe we'll put it under the microscope to see if we see any bubbles. Her mystery samples. In just a moment, she will show you just what that mystery sample was. Have a look and listen to Sabrina's description of this geological sample and see how you could add it to one of your groups. Which group did you add it to, and what characteristics made you place it in that group? What if it doesn't really fit into any of your current groups? Consider rearranging them or creating a brand new group to make it fit. All right, are you ready for the mystery sample? Let's see what Sabrina has to show us. Make sure you pay close attention and make lots of observations. I'll see you in just a moment.
Folks, remember when I asked you to stay tuned for a new geological sample to add to your groups? Well, this is what I've unearthed for you. I want you to sort this sample. This is a gray mudstone, a sedimentary rock made of compressed mud, so tiny sediments that are even smaller than sand. The mud was pressed against the bark of a giant ancient fern tree over 300 million years ago during a flood. Since the mud wasn't left out to the air long enough for the iron in it to rust, as happened with our sandstone sample from before, the sediments in the mudstone remained gray. This sample is too hard to scratch with your fingernail, but it's easily scratched with an iron nail. Not that you would want to. The sample feels slightly bumpy, but mostly smooth, with the imprint or the pattern of the fern tree that it was pressed against. The Discovery Center uses this sample to teach people about fossils and geology, though many other fossils like this are studied by geologists and paleontologists all over the world to better understand ancient life and ecosystems. All right, my friends, you have all of the information you need on our top secret sedimentary sample, so dig in.
Thanks, Sabrina. That mystery sample looks really cool, and it's amazing to think that it's millions of years old. Viewers, thanks again for joining us today and sending in your finds. Remember to share how Sabrina's sample would fit into your groupings using Flipgrid, Facebook, and Twitter. This gives you a bonus opportunity for your last entry in our Show Us Your Science contest. I hope you enjoyed learning about rocks, minerals, and making your own classifications. Today, we learned that minerals are the building blocks of rocks containing only one chemical compound, locked into that specific arrangement called a crystal structure. We learned that rocks can be formed in 3 different ways and are made up of more than one mineral, giving them their characteristic different properties. Those 3 formation methods result in igneous rocks, formed by the cooling of magma, sedimentary rocks, formed by many layers of sediment being squished and cemented together, and metamorphic rocks, formed by intense heat and pressure from the Earth. Thanks again for joining us today. I hope you had fun, learned lots, and continue with your rock and mineral scavenger hunt throughout life. You're never too old to find buried treasure. I'm Jillian from the Discovery Center, reminding you to keep digging and stay curious.